All right. Good morning, everyone. Can you guys hear? Can you see the screen?
Yes, sir. Good morning.
All right. Welcome to another MEC tutorial. Right. So this lesson, we're going to cover friction and how they can apply to certain static systems or systems in equilibrium. I think by this time you should at least know friction exists and understand a little bit about it. So let's just see how we would apply to these questions. All right. So let's consider we had this box here. Of course, this box would have a certain weight on it, yeah, and the forces that come with that, right? And then there's a normal force here, in line, but let's just offset it a little bit, back up. And we spoke about contact forces, and we know normal reactions. And if we were to try to push this, it would be a frictional force, right? Okay, so let's pretend this is something big, something very large, maybe a wardrobe or something like that. And you, a single person, try to push this really heavy wardrobe. It doesn't move, it doesn't budge, right? It's not going anywhere, right? It's not going anywhere, right? Then you call your friend, and both of you push, and then it starts to move, yeah? What happens here is that you had to overcome the force of friction, right? And through experiments, we found that the force of friction varies in some way related, let's call this Fr, the force of friction, to the weight applied onto the surface, right? Let's call this here. So you've come across this. This is the coefficient of friction. I Miss talked about this in class, right? Yep. So what this says is that the force of friction varies in some way relating to this constant, which of course comes about from these two contact forces and what type of material they are, right? Based on how much force is pressing these two materials together, right? So let's try and draw this a bit differently. These two forces here. Let's move this one up here and this one down here, right? So we can look at these two forces as the force that's pressing these two materials together, forcing them to be closer together, more of their molecular structure to contact each other, right? To be more in contact surface. And that's what creates more friction, right? And that's what's going to prevent us from pulling or pushing this thing, right? Now, the force of friction. If you yourself, and remember this is some big wardrobe, gonna go push and then it doesn't move. Now, because this system is in equilibrium, the force of friction is going to exert an opposite force to that. So if this was 6, the force of friction is going to push back 6. Because remember, the system isn't moving, right? Now, when both of you come to push, 2 people, I'm like 12, what's going to happen is that friction isn't going to push 12 like in most equilibrium system, right? It's going to push something under that because 12 caused this thing to accelerate, right? Cause it to accelerate. So as opposed to what you would expect with Newton's third law, you'd expect the force of friction to be something like 12 equal and opposite, but it's not the case, right? The force of friction varies with respect to this constant. Now, the way we get this constant is just through research, empirical experiments, engineers, scientists, physicists. what they did was they started to put materials together, try and push them, try and move them, apply forces to them, and see how they vary with respect to the weight and the force needed to move them, right? Now, in this course, we're going to talk mostly about the coefficient of static friction. That's the force needed to initially overcome friction and start this thing moving, right? The force needed to just overcome friction and get this box to move. So let's say maybe you were pushing at 2, at 6, and your friend came and also pushed at 6. That would completely overcome friction and put it into the kinetic zone. So coefficient of kinetic friction would start coming into play because this box would start accelerating. But based on these materials, we know that to initially start moving it, just get it to nudge a little bit to the side, right? Maybe some, let's bring in some calculus, some ds, right? Some small change, right? Coefficient of static friction would be something, not the entire 6, right? That your friend would bring, maybe something like 4, right? Maybe something like 4. Yep. So for these questions, we're going to focus on the coefficient of static friction, and they vary like this, simple, right? This here is a constant, these two. What we find is that as weight increases, as weight goes up, the frictional force goes up based on whatever that coefficient is. And this coefficient, of course, varies from the materials, right? From the different materials. Something like a smooth, polished wood surface is very different from a concrete surface, right? It's more rough. Another thing to note is that when it comes to work, right? So let's say again, we're pushing with 12 newtons and we overcome friction and it's sliding, right? If we were to kind of zoom in here, maybe on a closer level, we'd find that these things are rough, right? Surfaces are rough, they're not smooth. And so are those of the box, right? And what weight does, right? The normal force and the weight of the box is push these two surfaces together, yeah? Causing them to contact each other more and more. And when we try and push them, they grind on each other, right? They grind on each other. Grind on each other. Producing things like heat and sound. Heat and sound. So if maybe you rub some sandpaper on a piece of wood, you're gonna hear that sound. And if you rub hard and long enough, right, it's gonna start feeling hot, right? You're gonna start producing some heat. So in a system, right, with friction, when we're moving something, we're using some energy to move something, right? Some energy. Friction is essentially gonna do some negative work on that, right? Yep. It's gonna bring this body down to 0. So if this was coming at a certain velocity, this was already moving, right? Friction would slow it down till it eventually becomes 0. So in a closed system, looking at the energy of it from this box here, right, the final energy would be 0, but that energy is essentially going to things like heat and sound, right? So I think there's a question that asks about find the energy used to generate heat or something like that. So we'll use this principle, right? Okay. The only thing to take away from this, right? Keeping things simple, is this little formula here, right? So let's rewrite it. Let's say the coefficient of friction is equal to this frictional force, right? Frictional force divided by the normal force, yeah? Or we know this is the same as weight, right? That's weight, right? And we can say the coefficient of friction is the ratio of these two, right? The ratio of the horizontal force needed to move the box or the object divided by the weight or the normal force. Good. So let's tackle number 1. Knowing this formula here. So a sledge having a mass of 400 kilograms requires a horizontal force of 620 newtons. Keep it moving at a uniform speed along a horizontal surface. So A, calculate the coefficient of friction, and B, the direction and magnitude of the resultant reaction with the surface. So again, let's go back to a little diagram. Remember we were talking about contact forces, yeah? And how there's a normal force. And if you were to try and push this way, there would be frictional force. And then the resultant of the normal plus the frictional force would be the resultant force, right? So it would be something like this. So we'd want to find this angle here, yeah? So this angle is exactly what we would expect, right? This angle is tan theta, which is equal to the same frictional force over the Fn. I'll look more closely at the triangular forces. Yeah, but this here, we know this as just being the coefficient of friction, right? We can see how we can use the coefficient of friction to find things like the angle, and we can use these values with maybe Pythagoras theorem to find the magnitude. Let's set up our diagram. Here, we have some object, 400 kilograms, right? Downward, so we know weight. We just multiply this by 9.81, right? It requires a horizontal force of 620 newtons to keep it moving at a uniform speed along a horizontal surface, right? To keep it moving, it's not accelerating, right? We're just keeping it moving at a uniform speed. So what that tells us is that the system is in equilibrium, essentially, right? It's not accelerating. We're just keeping it moving at a uniform speed, right? If we wanted to find the coefficient of friction, we just use that same formula, which is developed, or that was given to us by scientists in physics when they did their experiments. And we say the friction, force, the horizontal force taken to overcome friction divided by the weight, or more simply, Fr over Fn, right? So we calculate the coefficient of friction. Well, we know the horizontal force to overcome friction is 620 newtons. The object weighs 400 kilograms. Put it into our formula, put it into our calculator, we end up with the coefficient of friction, mu, being 0.158. Now, also another thing to notice is that this here is unitless. So here would be newtons, right? And here, when we multiply out, give us newtons, and they would cancel out. Yep. And this makes sense because we don't want to multiply the weight by something with a unit to give us the force, right? Because that's going to change these intrinsic qualities. So coefficient of friction is unitless. Yeah. So no need to write anything here. Just write down the answer. Okay, and you can check this back on your own time. It should be right though. All right. So yeah, we've got these forces, we've got friction, right? We've got weight, and we know that if we were to put these forces together, they would form a force triangle. Yeah, because again, the system is in equilibrium. And this resultant here is the frictional force, right? Because remember, this here is the force to overcome friction, right? And so the frictional force would be this way, yeah? And the normal would be here, right? Because the weight is this way, the normal would be here. That, creating this here, this resultant, yeah? Resultant here. Where that came from. We take these, we put them into a triangle, very simple triangle, horizontal force, weight acts vertically downwards, right angle. We can find the magnitude, right? Here, we can find the magnitude of this and direction. So we find the direction by using tan of the angle that's called as phi, phi is equal to, well, 620, which is F, divided by W, right? And well, we know that this is this. So we can just plug that in right here, right? So then this would become tan inverse of 0.158. Yeah, simple. And this here is approximately equal to 9 degrees. So nothing too difficult. So the direction is down. What else do we need to find? We need to find the magnitude of this force, right? And we already found the coefficient of friction. What is the magnitude? Well, we know two sides of a right angle triangle, so we can use Pythagoras theorem, right, to find the hypotenuse. So what is that? That's here, your weight squared times the force to overcome friction squared, and we square root all of that. So R is equal to the square root of 620 squared plus 3,924 squared, and that's equal to 3,972.67 Newton. And you can check this back as you work along. Okay, so any questions on this one? Very simple, right? Okay.
So I got a quick question.
Yep.
The sign mu, is mu you call it? The little u sign like, or M kind of shape?
Yeah.
Yeah, that sign. What does it represent again?
The coefficient of friction.
Coefficient of friction. Okay. And for the direction and magnitude of the resultant reaction to the surface, this is the angle in which it force is being okay. Just want to confirm. All right.
That's the angle there, right? And we move over to our triangle.
Yep. Yeah. I understand.
All right. Good. Now let's do number 2. And number 2, we could finish in one line. Right? So a 2-ton mass rests on a horizontal surface. Calculate the horizontal force in kilonewtons required to move this mass at uniform speed along the surface if the coefficient of friction is 0.35. So we know mu, yeah, and we know that's equal to the horizontal force required by friction, right? Divided by the weight. So we know mu and we know weight. Take a few minutes, work this question out, and tell me if you get the same answer as me, right? Let me go get some water. Okay, anyone finished? No? Right. No one's finished? No one got this answer?
Yeah, I got the answer.
Okay, good. Right. First thing we need to do to find this force, this one here, right? This is the question. This is what we want to find, right? Calculate the horizontal force in kilonewtons required to move the mass at uniform speed along the surface, right? So solving this, we get, mu W equal to F. That's what we do here, right? So the mass is 2 tons. Multiply that by gravitational constant times the coefficient of friction to give us the force, and then dividing by 1,000 gives us kilonewtons, right? Another way you can do this is simply just put this here as 2, right? Which would be dividing this entire thing by 1,000, right? So 2 tons divided by 1,000, and it will give your answer right away in kilonewtons. So you can skip this step if you want it. Just put 2 here. So I don't suspect there are any questions on this, but if you have any, you can go ahead. If you had trouble finding the answer. Okay. All right, so I'll just move on. A body having a mass of 40 kg rests on a horizontal table, and it is found that the least horizontal force required to move the body is 90 newtons, right? Horizontal force required is 90 newtons. What is the coefficient of friction? And part B, how much work is done in moving the body along the surface of the table through a distance of 3 meters, right? So part 1, coefficient of friction, we have a formula. The horizontal force required to move the body is 90, right? The weight is 40 times 9.81. Again, putting this into a calculator, you end up with the coefficient of friction being 0.229 or 0.23. Okay, Nicholas, go ahead.
Yes, sir. Quick question. With regards to multiplying the weight by the 9.81, if the weight wasn't given as kg and it was given as pounds per se, would you have to convert to kg before multiplying by 9.81?
If the weight was given in pounds?
Or any other unit of weight except kg, would you have to convert to kg before you multiply by 9.81?
So this gravitational constant, right, is how it came about is that, well, we measured how much force, right, how much force is applied by 1 kilogram of mass. So we found a 1 kilogram mass, right, a 1 kg mass would apply downwards 9.81 newtons, right? So we use this experiment, and this, of course, would change throughout the world. I think like in Guyana around the equator, this is more something like 9.79. Yep. And more around like Europe and stuff, it would be 9.81. So that very depends on the gravitational field of the Earth. So, but this here, right, we use this to abstract one level and say that 60 kgs, right, is the same 9.81, that same constant, newtons per kg, right? So if 1 kg gives us that much force, then 60 kg should give us 60 times that much force, right? So that's how we end up with this. So yes, you would need to change. Okay, John, raise your hand again.
Yes, sir. No. I get it. I understand.
Okay, good. Right, so this here is a constant, and it's what we use, this here. It might not be specific to Guyana's location, right? And this constant changes throughout the gravitational field of the Earth. The book uses this one, so for simplification's sake, we use this, right? But it's important to know that this constant comes from this, right? 1 kg exerts that much force. Yep. So I think for PSI or something, yep, a different force, the imperial is 0.522, something like that, you know? In the oil industry, actually, they use this. Yep, 0.522. So maybe if you go work in the oil industry, you might see something coming up like it, right? 0.52. And if you just work out your units, calculate your pounds and whatever, and convert from maybe not newtons anymore, something else, a different unit of force, then you'll get different numbers, right? So this is just a constant based on those units. All right, so how much work is done? Moving the body along the surface of the table through a distance of 3 meters. So, well, we know that we used 90 newtons of force to move the body along 3 meters, right? But what is work? Well, work is the way we quantify using that energy, right? We say we use it to do this much, right? So we use that force to move 3 meters, right? So how much work is that? Now, if we use some force X to move something really big, 3 meters, right? 3 meters, that's different from using something smaller, like let's say something weighing Y, 3 meters, right? You probably do more work moving X. So the way we quantify that is just by using the force we use, the actual amount of force, times how much we actually move, right? How much work. And again, if we were to move something with the same force, but if we were to apply it, moving it 4 meters, moving something 4 meters versus moving something 3 meters, right? We'd say we do more work here, right? We accomplish more. So work is just the way we quantify what we've done with energy, right? And how we do that is just by multiplying the force by distance, right? So another formula, keep in mind, work, right? This W here now is work, not to be confused with weight, right? Not weight, is equal to force times distance. And simply, the unit for work is joules, right? Or Newton meters, joules, right? So just multiply 90, which is the force you use and how long you use it for, right? So 90 times 3 meters, 270 joules. And that's it, number 3. Any more questions on number 3? No. All right. Number 4. A wooden tray rests on a horizontal surface, and it is found that with a mass of 3 kg in the tray, a horizontal force of 10 newtons is just sufficient to cause the tray to slide. When the 3 kg mass is replaced by a 7 kg mass, it is found that the horizontal force required to cause the tray to slide is doubled. Calculate the coefficient of friction between the tray and the surface and the mass of the tray. Right? So what we need to calculate is the coefficient of friction. Let me zoom in here a little bit. And we have a little formula that we got. But what we notice now is that something, right, some tray, which of course has its own weight, right? The tray has its own weight, and there's a mass resting inside that tray that also has its weight. That also has its weight. And that it's sliding on some horizontal surface, right? And that horizontal surface on that tray has some unique coefficient of friction. But the weight now is something modular, right? Because it's comprised of two things. Okay? Comprised of two things. The weight of the tray plus the weight of this object inside, right? The weight of the mass inside the tray. So now, even though the tray is contacting the surface, right? How much force holds these two things together, right? The force holding the tray to the surface varies with respect to the weight, to the weight. So, okay, two persons are raising their hand.
Excuse me, sir. Good morning.
Yeah.
Okay, can you please put that back over?
All right, yeah. Jarek, Kanar Jarek.
Yes, sir.
Yeah, what's your question?
I'm asking if you could please go back over the diagram.
Oh, this little thing that I drew here. All right, cool. Let me start over. Let me open up Paint. Let's get it. Maybe I was moving a bit too fast. No worries. Okay. Some space here. Maybe this is a tray. Go to one side, make a tray. And let's put some mass. So this mass is 3 kg. Yeah. Okay. Good. So let's pretend this mass wasn't here and it was just the tray, right? The tray and the ground. So we know the coefficient of friction, right? The coefficient of friction. Well, that's equal to the force required to move the tray, right? To overcome the friction, which would be F, and that varies with respect to the weight. So let me write it this way first, right? The frictional force varies with respect to the weight, right? More weight, more friction, right? Driving these surfaces together, right? Driving these surfaces together, causing them to contact more, right? So more force pushing these rough edges together, right? Creating the friction, right? Yeah. So if we add more weight in it, this of course is gonna go up, right? This of course is gonna go up. Yep. Driving them closer together. And when you try to push them, they form like little weak intermolecular bonds. And then you break those bonds and they generate heat and sound and all these kinds of things, right? So we know our formula, yeah? So let's forget about this mass. Don't worry about this mass. It's just your tray and the force required to move the tray and the coefficient of friction, right? So let's say the weight of the tray was T, yeah, WT. So the force required to move the tray would be WT, right? And that would divide F divided by WT, which is the weight of the tray, and that would be equal to the coefficient of friction, right? Everyone should be okay with this, right? We're not worried about mass. This is it, good. So now, if we were to put something, let me write this back. F, weight of tray, right? W sub T, right, as equal to the coefficient of friction. And we don't know how much force it takes to move it when it's just the tray, right? We don't know. We don't know this. But let's say we put the mass in, as the question suggested. Let's go back to the question. A wooden tray rests on a horizontal surface, and it is found that with a mass of 3 kg in the tray, horizontal force of 10 newtons, just sufficient to cause the tray to slide. Yep. So when we put in the 3 kg, what happens? What happens here, right? Friction should go up because weight goes up, right? Weight goes up because we're adding this mass, right? So this weight here, and its formula is not just the weight of the tray anymore, it's the weight of the tray plus the weight of this boulder or this mass, right? Plus the weight of this mass, yeah? Wm, which is, of course, we know 3 kg, but let's generalize it, right? So remember, this here is the constant, yeah? And this here varies with the weight, yeah? As weight goes up, this goes up. So here, let's call this F1 or Ft, yeah, for the tray, right? And this here is T plus M, right? They say, call this T2, okay? So this here, let's call this the second horizontal force. This is the one with the weight inside, right? So this W is not just the tray anymore at the bottom, right? This here is that plus Wm, right? The weight of the mass is equal to the same coefficient of friction, right? Because when this goes up, but this here is the coefficient of friction, right? It's not changing, it's unitless, and it's based on the materials. So is everyone okay with this formula? Yeah?
Yes, sir. Yes, sir.
Okay, good. So now back to the question. So mass of 3 kg in the tray, a horizontal force of 10 newtons is just sufficient to cause the tray to slide. When the 3 kg mass is replaced by a 7 kg mass, it is found that the horizontal force required to cause the tray to slide is double. Calculate the coefficient of friction between the tray and the surface and the mass of the tray, right? Good. So we created a new formula, right? Which is essentially just this formula, F, but we expanded what weight was, right? Weight of tray, weight of mass, okay? Weight of tray plus weight of mass. Yeah. Now we can break this down even further, right? And say this is the same F on top. And this weight of tray is, of course, the mass of the tray times gravity, right? Mg. Yep. Mg. And this here, the weight of the mass is of course mg2, right? What we can say is the mass of the tray, let's just call that T, plus the mass of the mass, let's just call that M, times the gravitational constant, right? 9.81. And this is the formula we want to work with, right? This is the formula we need. Now, of course, you can keep it at this level here, this level, this formula, and work here accordingly, and you should get the same answer. But me, I like simplifying things and keeping it like this, right? So, yeah, calculate the coefficient of friction between the tray and surface. So find mu, the coefficient, and find the mass of the tray. So, putting this in terms of the question, when the mass is 3 kg, I'm a mass of the mass plus mass of the tray times 9.81, right? Which is this, right? We break that down sufficiently, right? The horizontal force is 10 newtons. A horizontal force of 10 newtons is just sufficient to cause the tray to slide. When the 3 kg mass is replaced by a 7 kg mass, it is found that the horizontal force required to cause the tray to slide is double. So here, double. Yep, 2 by 10, double. Calculate the coefficient of friction. Well, we know that the coefficient of friction is of course equal to this, and this is of course equal to this, because the coefficient of friction is, again, constant, right? It's not changing, because the materials aren't changing, right? Yeah. So this should be equal to this, right? Now, solving this for x, let me break down how I solve that. First, what I did, divide by 10, both sides, multiply by 9.81, both sides, right? Flip, carry over. So let's break that down here. 1 x plus 3, 2 x plus 7. Yep. Reciprocal of both. This is x plus 3 is equal to x plus 7 divided by 2, multiply by 2. Multiply by 2, 2 times x plus 3. Distribute. 2x plus 6 is equal to x plus 7, which is what we have here. Skip a few steps. Now, solving for x, right, is as simple as 2x minus x is equal to 7 minus 6. So we can say x is equal to 1. And what is 1 in terms of? Well, we factored out the 9.81, right? Yep. So it's not weight anymore, right? It's not weight anymore. Okay. X is 1 kg. X is 1 kg. If you worked it differently and you kept the 9.81 in here and you multiplied your 7 kg times 9.81, you would end up with weight, right? And then you divide by the 9.81 again to find the mass of the tray, right? So great. One goal, the mass of the tray. Now, knowing the mass of the tray, we can simply find the coefficient of friction by just substituting the mass of the tray, which was the unknown, yeah? So substituting in that 1 kg into our formula, yep, 1 plus 3, which is total mass, right? Total mass times the 9.81 divided by the force required to move it is equal to 0.255. And again, this is unitless, the coefficient of friction. Okay, all right. Any questions on this? No? As long as you break it down and get the formula and set it up, right? Should be pretty easy. And a more intuitive way.
Sir,
Yeah, go ahead.
sir, side and equal sign the same, sir. Because if you watch the trade, x plus 7, right? And 2x plus 6. So 2x, to make both of the sides equal sign the same, right? X will have to be equal to 1. Because 2 times 1 would be 2, plus 6 would be 8. And x is equal to 1 plus 7 would be 8. So x would have to be equal to 1 to make it the same. Could write it like that, or that one to substitute.
Are you breaking
Sorry,
up?
I'm saying?
What are you saying? No. Are you saying this is wrong?
No, sir. No.
Okay, are you saying there's a different way to solve it?
I was thinking that, sir, but never mind.
All right, and any other questions? You can
get 39.81.
Oh, I fucked it up.
Use it as.
I fucked it up, right? So another way you can think of this is that okay, so this here, right? This here, we know as F over weight, right? And weight is the mass, right? Times the 9.81, yeah? 81.
Yeah.
Now the mass is not just this mass, is the mass plus the mass of the tray. So we just put x plus 3 times 9.81. So that's essentially what we got here, right? Essentially what we got there. Agreed?
Yeah, CD factor.
Okay, yeah. But, or you could, here weight plus weight is some mass, mg, right? Plus this mass, mg, right? So factored out the g, the gravitational constant, we got the mass plus the mass times g, yeah?
And then you wrongly 9.81 to 10 and then cancel it out.
No. So
how you get it out?
Okay. So we divide by 10, right? So divide by 10 here. Divide both sides. Add in a 10 here, right? Right. This is multiplying, right? Okay. So 10 into 20. Yeah, this is 2. 2 left. Great. And you remember you gotta divide both sides of the equation. Let's not worry about this right now. Don't worry about this. Divide both sides. So this side you gotta divide by 10 too, right? 10.
Yeah.
Okay. 10 into 10, 1. Great. Good. Now we could do it the secondary school way and say we carry over this 9.81, right? Carry, you remember dividing here, carry over, and you multiply by 9.81 here, right? So multiply by 9.81, and they cancel out, yeah? Right? They cancel out. Or you could do it the university way and say that this is a mathematical equation, and we multiply both sides by 9.81. So multiply both sides by 9.81, 9.81 here, 9.81 here, right? what we do on this side, we need to also do on this side. Cancel out, yeah? Cancel out. Cancel out. And that's how we end up with 1 over the x plus 3 times 2 over x plus 7. Okay? Okay, good.
All right, just see you, sir.
All right, good. So the guy that was asking a question, your mic was breaking up a little bit, so you could type it in the chat and I'll check it and maybe I could answer it. All right. So any more questions on this, right? We get x as 1.
Sorry.
Yeah, okay, go.
Yeah, sorry, you're doing the work done or your user part is it?
No, I reached the part yet.
Okay. The guy said it's okay.
All right, good. All right. Okay, so we know coefficient of friction. We know mass of the tray. Now we want to find something else, yeah? We want to find what would be, I made a mistake here.
That's why I asked you, sorry. I looking at it and I wondering how this is,
Yeah. Yeah, sorry about that. I'll change that for a second. Yeah. Anyway, so we found x. Don't worry about this yet. We found x and we found the coefficient of friction, yeah? What would be the work done in moving the tray through a distance of 5 meters with an 11 kg mass in the tray, right? So we know work, right? We know work is that force we use and how long we use it for, how much we accomplish, right? Force times distance, yeah. That's the way we quantify work. Quantifying how much energy is used, right? So good. So let's find the force, right? So we know the coefficient of friction, mu, is equal to force, right? Divided by, or the frictional force, right? Divided by the mass times the gravitational constant, or divided by the weight, yeah? And we know weight is the mass times 9.81. 9.81. And we know that this mass, is the mass of the tray, right? Which is 1 kg plus this 11 kg mass in the tray, right? Plus 11. This is this. Solving for F, we get F is equal to the coefficient of friction times this thing at the bottom here, right? So this times this. So we could write it 0.255 times the 1 plus 11. Well, let's write this 11 plus 1. 11 plus 1, which is total weight. You could just go straight ahead and put 12 kg times 9.81. Okay, so, all right, Amart, so you answer your own question. Good. Good. So yeah, the question is asking with the 11 kg mass in the tray, right? So we can accept this, right? Solving this equation, we found the coefficient of friction, we solve for force. This is good, right? And of course, we replace this 11 plus 1 to 12. Yeah, to 12. Good. And when we solve for force, we know work. What's the work done? Work is equal to this force times the distance, okay? And what is that distance? The distance is 5. That distance is 5. So we just multiply this entire thing by 5.
Sure. So mu for the 4 kilogram mass would be the same as mu for the 12 kilogram mass.
Mu, what are you saying?
Mu for the 4 kilogram mass would be the same as mu for
Yeah,
the 12 kilogram mass.
Yeah. Yeah. Because mu is based on the materials, right? So let me,
Not based on the mass.
the force is based on the mass.
Oh, okay.
See if I can Google something really quick. Or actually just search it. All right, let's just bring this up. Let's get this bigger. All right. Okay, good. So you guys see this? So different materials have different coefficients of friction, right? So steel on steel, steel on steel, rubber and steel on steel together, the coefficient of friction is this, and this is found by experimentation, right? Aluminum on steel, this is the coefficient of friction. Copper on steel, this is the coefficient of friction. Rubber on concrete, dry, right? This is the coefficient. Rubber on concrete, wet, this is the coefficient of friction, right? And remember, we talked about coefficient of static friction versus coefficient of kinetic friction. This is to get it moving, and this is once it's moving, right? So you ever realize you're trying to push something, right? And you push it, but to start it off initially requires a little bit more effort. But once it starts moving, it's easier to push. Well, that's because the coefficient of kinetic friction for most materials is less. Yep. So here, when weight goes up, the force required to overcome friction goes up, right? But this here always stays the same. This tells us by how much this goes up, right? If this goes up 1 kg, okay, this doesn't go up 1 Newton. This goes up based on the coefficient of friction. So the coefficient of friction, as long as the materials aren't changing, right? The intrinsic properties of materials aren't changing, the coefficient of friction won't change. It is the coefficient of friction. So if mass change, we don't care. Coefficient of friction is the same, right? So yeah, this here is W. Yeah. Okay. And remember, if you guys going through and you find a mistake or maybe a typo or something like that, tell me so I can notify the rest of the class, right? Because I usually just make these handouts the night before while I work through the questions, right? So they're definitely gonna have maybe a mistake or a typo inside them, right? If you find mistakes, email me so I can tell the rest of the class. So yes, again, to answer your question, the coefficient of friction is based on the materials, right? Based on different materials, on 8, 0.1.
So a quick question.
Yep.
Like, let's say for finals, and this, like, if a specific question come with the same coefficient frictions for the specific materials, you would have to use it for reference certain questions. If you understand what I'm saying. In the future, I know.
Like if the in the future, yeah, in the future. So
yeah.
Well, I'm an electrical engineer, so this stuff is more like for civil and mechanical people. But yeah, so like if you're going, gonna be a mechanical engineer and maybe you're designing engines, right? You'd want to know how these different metal parts would rub together in maybe an engine block and stuff like that. So yes, you would have to reference tables like these, pull them out and do your calculations. And even as a civil engineer, right?
Yes, sir. Okay, sir.
As long as you're gonna have moving parts and you're gonna have friction, you're gonna have to reference tables like these. So yeah, something to start thinking about.
Yes, sir.
If you have more questions.
Another quick one, sir. Another quick one.
Yeah, go ahead.
Yes, sir. We're supposed to get next mini quiz on Friday. So I was wondering, like, what exactly would the quiz be coming on?
Well, at the end of the class, yeah, I'll tell you guys. Let me start number 5.
All right, good, sir.
A block. Okay. A block having a weight of 300 Newton rests on a flat horizontal surface. The coefficient of friction between the block and the surface being 0.25. Calculate the magnitude of the horizontal force which will cause the block to slide over the surface. And B, if the block slides in the direction of the applied force with a uniform velocity of 1.5 meters per second, calculate the heat generated by friction in joules per minute. Okay. Yeah, anywho, so to find force, same formula, coefficient of friction, the force to overcome friction divided by weight. Weight was given to us here as 300 newtons, okay, 300 newtons. Coefficient of friction 0.25, so that's 300 times 0.25. 0.25 is essentially a quarter. So a quarter of 300, you can plug this into a calculator, it'd be 75, right? So a quarter of 300, half of 300 is 1/5, half of that is 75. Yeah. And you can plug it into a calculator and verify. So that's finding the force, right? Calculate the magnitude of the horizontal force, which will cause the block to slide over the surface. Okay. If the block slides in the direction of the applied force with a uniform velocity of 1.5 meters per second, calculate the heat generated by friction, right? So remember, as I said, some velocity, something with some momentum is coming. All right, there's a question in the chat. What's the formula for finding P? P, well, I think in the book they have F, this horizontal force is P, right? So coefficient of friction is equal to P divided by W, where P, remember, these are just placeholders essentially. They're variables and we assign meaning to them. So this, where P is the horizontal force, right, required to overcome friction, yeah? Yeah, so just remember that these are just, you know, little placeholders. So this here is P. I just say F. So calculate the heat generated by friction in joules per minute. Okay, good. So remember, as I say, if something is moving along at the speed of 1.5 meters per second, and all the time through sliding, right, friction is just grazing away at the bottom of this material and generating heat, right? Some heat is coming off here, right? So the thing is, as we do work in this direction, right? As we do work in this direction, friction is essentially doing negative work, yeah? Negative work, trying to slow this thing down. So if we run and we push a box, it's gonna slide and eventually it's gonna come to a stop, right? Because one, you only push it, you didn't continue pushing it. The force isn't continuous. And after that initial push, it accelerated and friction is gonna start to decelerate it, right? It's gonna do negative work on it, right? And most of that work, remember some goes to sound, some goes to heat, all different things, but let's generalize and say 100% of the negative work that's done by friction, or almost 100%, is equal to the heat, right? It goes to heat, And now the units for heat are calories, but they want it in joules per minute, and heat is just another way of saying work, if you guys get that, right? Because we're just assuming that 100% of the energy that friction takes away goes to producing heat, right? The negative work that friction does goes to producing heat. Yeah, so work, there are 2 units for work, if you guys remember reading that work. One of them is in joules, yeah, joules, and the other one is calories, right? Calories. And we know calories is also a unit for heat, right? And we know we go on a treadmill, we run, what are we doing? We're burning calories, right? Burning calories, producing heat. We're doing work. So essentially, what they want us to find is work, negative work done by friction per minute, right? So how do you find work? Work is equal to the force we use, so this here would be the frictional force, times the distance. So per minute, we would do some amount of joules. So every minute, how many joules do we burn? Well, we need to know what distance we travel per minute. So if this is the velocity, 1.5 meters per second, then for a minute, we would travel 1.5 meters times 60, right? Which is equal to 90 meters per, not 90, yeah, 90 meters per minute, yeah, per minute. That's the distance we would travel in 1 minute. Now, if that's the distance, and F is equal to 7 to 5, and we multiply that by that,
So,
and we can find heat.
so it will be 90 meters per second.
No, because we're multiplying by 60, right? 60. You get that? Do you get converting meters per second to minutes? So if 1 second, we move 1.5 meters, right? Then for 1 minute, we move 60 of these, right? We move 60 times 1.5, which is 90. We move 90 meters every minute. Yeah. So let me break down this calculation and
Sir, you
Oh,
gotta
yeah,
break down
I realize I made a
the
mistake.
velocity
Yeah, I made a
formula.
mistake.
all right. So let me put the units in. So 1.5, right? Meters per second. Yeah. And we're converting it. So 60 seconds, right? Over 1 minute. Yeah. Does that make more sense? Yeah, because this is just multiplying by 1. So this second and this second will cancel out, and we're left with per minute. Yeah. Okay. All right, good. So we got our distance, and the previous part we calculate our force, right? So work, or negative work, heat is equal to that same FD. So F, as calculated 7 to 5, times the distance we moved, right, per minute, would give us joules per minute, right? times 90, right? And this should give us 6,750 joules per minute. Joules per minute. Okay. Okay. Okay, so any questions about this?
One quick one, sir.
Yeah.
Even though they say heat generated by friction, they basically mean work done. This basically it. It's just like another way of saying find the work done.
Because what exactly does friction do? Friction just trying to slow down this box, yeah? And generating heat in the process. Friction ain't doing much, right? Maybe
That's what I understand.
the little trickle, maybe 90% goes to heat and a little 10% goes to sound. You could research it a little bit more, find out how much of the energy from friction goes into heat. Yeah?
Yeah, actually, it's just like a trick thing because if you use the definition, energy is the ability to do work. So heat is energy, and energy equal to work. So you still gotta use the work formula.
Yeah. Two other persons raising a hand. Go ahead.
Excuse me, sir. I was wondering where we got the 75 from.
From the previous working, right? This will work in here.
Oh, thank you, sir.
Say work down, stick it in here. Yep. All right, anything else? I think someone messaged in the chat. Let me check. Is joules per minute considered watts because it's work over a period of time? Well, you wouldn't say watts, you would say power, right? So this person messaged me privately. Would joules per minute be considered watts? Well, watts is a specific unit, right? But power, yeah, you can't think of this as power because it's in per minute, which is weird. Per minute, which is the work done for a period of time. So it's like how much power is used. Yeah, so in a roundabout way, you can think of this as power, if you like. But they asked us specifically for these units, right? So this is what you want. Okay. So no more questions on that. Let's continue. Okay. All right, this question is weird. Let's skip this one. And you guys can research steam engines and valves. But the working is pretty simple. You can work on that. But that's going to leave with me teaching you some other stuff. But essentially what I did, let me just run through it really quick. Sliding face of a slide valve of a steam engine is 150 millimeters by 300 millimeters. And the steam pressure on the back of the valve is 1,200 kilonewtons per meter squared. If the coefficient of friction is 0.02, what is the force required to move the valve? So essentially what I did is coefficient of friction equal to force required to move the thing divided by the force holding them together, right? Remember, this is not weight. This is the force holding them together, right? And the force holding them together is based on this pressure. So pressure equal to force divided by surface area, right? So if we multiply that by the surface area, we can get the force. So multiply that by this, right? And then of course, carrying over this this W here. Well, it's not W anymore. It's steam force, Fs. Yeah? So we can just say mu times F. The force holding the two things together is equal to the force needed to move them. Right? You guys get that? It's not very intuitive to think about it without knowing what a slide valve of a steam engine is, but you can work it without knowing what it is. So do a little research, check this out, but remember, focus on the test. Try not to worry about this. I really doubt Mrs. Silva will bring this question, right? So don't worry about it. If you want a little extra work, you can look at it, right? But don't worry about it. Let's move on to number 10. So numbers 7, 8, and 9. Some of them are graphically. One, I think, is just an extension of what we've been doing, like in numbers 1 and 2 and 3, right? But number 10 is the one you might want to focus on for the test, right? So number 10 and maybe 4 and 5. Yeah, 4 and 5. So number 10 is one you want to focus on for the test, right? 10, 4, and 5. One of those. I don't know which one. And, you know, as we work, you can kind of see which one would test yourself the most. So that one would be most likely to come. Okay, so good. A body having a weight of 150 newtons is resting on a horizontal table and can just be moved by a horizontal force of 25 newtons. Calculate the coefficient of friction and the direction and magnitude of the resultant reaction of the table. Yeah, okay. So simple basic formula again. Mu F divided by W. The weight is 150. The horizontal force is 25 newtons. 25 divided by 150, well, that's 1 upon 6. 1 upon 6 in decimal is 0.16667 approximately, right? So this here is a coefficient of friction. Okay, so calculate the coefficient of friction and the direction and magnitude of the resultant reaction of the table. Direction and magnitude, remember, for force triangle, you can have a look back at number 1. W, right? Coefficient of friction. Finding theta, tan theta, tan theta, let me write this back. Tan theta equal to coefficient of friction, right? F divided by W. So let's just call that 0.16667, right? So theta, or as the book could write it, phi is equal to tan inverse of this, which is approximately 9.5 degrees. And then to find the magnitude of this line, horizontal force, vertical weight, 90 degrees, Pythagoras' theorem, the resultant, the magnitude of the resultant is equal to the square root of 25 squared plus 150 squared. And that, plug it into the calculator, what do you get? 152.07 newtons. Yep, 152.07 newtons. Good. No questions, right? This is simple. At least this part. Now, the second part of number 10 is a bit more complicated, yeah? So the second part, so same question, same weight, but a continuation. If the table were acting at an angle of 20 degrees with the horizontal, what would be the value of the force that could just move the body, and what would be the resultant reaction of the table. Okay, so a bit different, yeah? So let's draw some stuff here.
So, sir, even if the angle change, the frictional coefficient would stay the same.
If we what?
If the angle change, the coefficient of friction, would it stay the same?
Yes, but your weight would change, yeah?
The weight.
So let me draw it out and I'll show you. Because, yeah. So some mass, this paint look a little ghetto compared to the other one. Anyway, yeah, okay, good. So we have force pulling at some angle, right? Weight coming down. And we know no matter what, contact forces, right? The reaction should be something like this. As long as this is going. So this is a system we're familiar with. Now, the reason why I wouldn't want you to just go up and assume that the coefficient of friction is the same, because it does stay the same, but there's something more, right? This here is two components, right? A vertical and a horizontal, yeah? Vertical and horizontal. So what you find is that this magnitude here, right? This magnitude here, and this is going down, is that this is gonna take off some from this, right? It's gonna essentially remove some of the shorten this, right? So coefficient of friction would stay the same, but you would end up with a very different equation. You'd end up with a different F, right? A different F, and a weight that isn't exactly described. Weight minus some maybe F sine theta. But this is a rabbit hole, and this isn't what you want to go through. So yeah, coefficient of friction would stay the same because it is the material and you are changing the angle, but it's just the material, right?
Okay.
But yeah, this equation, the regular one, mu, equal to F over W, right? Wouldn't hold. This wouldn't be true anymore, right? Because F is a completely different thing and W is a completely different thing because of how these vectors work out, right? So this equation wouldn't work out.
You got input for angle.
Yeah, because we include an angle. So this angle here is 20 degrees. So let's not go down this rabbit hole. Let's avoid that. This angle here is 20 degrees. And let's use these three to create a fourth triangle, yeah? Simply enough. So let me put over here. How do you rotate? Okay. So let's use these forces and create a fourth triangle. So this here is a W, right? W hanging down. This here is that pulling force here, F. And this here is your resultant, right? R. This angle here, 20. Vertical here, sorry, vertical, W, horizontal. This here should be 90, so inside here is 70, yeah? 70. You good?
Yeah,
now,
yeah, you got the 70.
Now, okay, good. So the coefficient of friction, actually, describes with this horizontal component, and it describes this angle, right? Just remember, this coefficient of friction that we found is also tan of phi, right? Tan of phi. Tan of phi. So phi, because again, coefficient of friction is the same, yeah? So using phi, finding this angle is 9.5. This is the angle the resultant makes with the vertical, right? So the resultant makes an angle with the vertical. With the vertical. Right? That's this angle. So, okay, good. So this angle here is that same phi, which is 9.5, right? 9.5. This angle here is also 9.5, right? Rudimentary by now, very trivial. Here, easy. The three angles in the triangle, the sum of the three angles in the triangle equal 180, right? Add these two up, we get 89.5, 89.5 subtract. Is it 89.5? No, 79.5 subtract 180, this should be 105. 100.5. Yeah. 100.5, right? Okay. So we have a triangle. We have our angles. We have one magnitude, which is the weight. Force changed completely. Yeah. Force changed completely. And we know it can't just be that same force we had before, right? It can't just be the same 25 because the weight is changing, right? Because of that vertical component. So F now is an unknown. F is an unknown. This is the same triangle, right? This here is W and R. So, well, the same thing we've been doing throughout this course. Law of sines, sine rule, set it up. Okay. W over sine 105 is equal to F divided by sine 9.5, which is also equal to R divided by sine 70. Yeah. So we set up our equations, solve for F, solve for R. Right? So take 2 minutes, find both, and tell me if you guys get the same answer. Right?
Now one question, so I get 150.
It's 152.544. Here?
No, so the 150 over sine 100.5. The 150, sir.
Oh, okay. Yeah, so a body having a weight of 150, yeah? Body having a weight of 150 is resting. So the weight of the body doesn't change, does it? No.
No, so yeah, I understand.
Yeah. What would be the value of the force that could just move the body? Is the body is the same body we're talking about. So the 150 stays the same. Yeah. So remember, don't go into this rabbit hole here of trying to resolve these and things, because a lot of other things would come into play and you'd end up with some very weird stuff. Okay. Better to just do the force triangle way, the things we've been learning, and solve that. So double check this for me. And if you have any questions, go ahead. I'll be right back. Okay, I'm back. All right, there's one question in the chat. No one didn't ask anything while I was gone, right? Okay, so Steve says they're correct. All right, good. So if you don't have any questions, that's it. That's all I have for you. You can leave. If you have some questions, go ahead, and I can try and clear it.
Yes, sir. Remember you tell me at the end of the class you would tell me which one, sir?
Yeah, didn't I just say, right? So focus on number 10, number 4, and number 5, yeah?
Very good, sir. Thank you.
Yeah, 10, 4, and 5. All right. And remember, be prepared for anything, right? Because Mrs. Celia, she brings the test easy, but you never know. Maybe she might not be in a good mood and decide to bring a really hard test.
Excuse me, sir. How did we get the 152.544?
Well, we divide this. We divide this out, yeah? And then we carry over and multiply, yeah? Which is these? You can do it a different way. You could keep this whole if you want and solve it this thing, you know? As long as you get the same final values, right, for R and N. You don't have to do it this way. What I did is I work this now. So yeah, 150.
Yes, sir.
Yeah, go ahead. Someone saying something? Very good. That's it.